direction. So how do we talk about the direction of a vector? How do we represent that? Well, one way to do that is by giving a vector that quote unquote has no magnitude. What does it mean to have, obviously you can't not have a magnitude. So what we do is we say, give it a magnitude 1. And I'll show why that's useful in a second. So this is called a unit vector. Length 1, 1 unit. Okay. So to turn a vector into a unit vector, you simply take it and you divide by the magnitude. So suppose you have a vector v, and you want to turn it into a unit vector u, but in the same direction. So you start with that vector, and you simply divide by the vector v, you simply divide by its magnitude of v, and you get this unit vector u. Okay. So let's do an example. Okay. So here we've got the vector 5, 1. So let's find the unit vector. So let's find both the direction and the magnitude. So direction represented by a unit vector. So how do we do this? Okay. So the unit vector, actually, it's going to be easier to find the magnitude first. Because notice that we need that to find the unit vector. So, okay. So what's the magnitude?
It's 5 square, 4 square,
So the magnitude is square root of 26. Okay, great. So now let's find the unit vector. So the unit vector is, well, we just take the original vector and then we divide by the magnitude. So I like to write that as a constant out in front. So there you go. And if you want to check yourself, you can check using a calculation that's going to give you something of magnitude 1. So notice that this is the same as having the vector 5 over radical 26, comma, 1 over radical 26. That's what it means to multiply by the number by having the number in front. Okay, so why is a unit vector our choice for indicating direction? Well, it has this nice little property. So if you have a unit vector u and some positive number c, then if you take that number times the vector, so c times u, the magnitude of that is just the magnitude of c times the magnitude of u, but we just said u is a unit vector, so its magnitude is 1. So in other words, the magnitude is just c. So in other words, you didn't need u at all to say what the magnitude was. Does that make sense? Okay. So from c times u, the magnitude is just c. So this is why in a sense we think of c, or there being some number that's just the magnitude, and u, the unit vector, is like pure direction. And this is the sense in which it does not make any contribution to the magnitude, but obviously it's a vector, so it has a direction. So this is why unit vectors are going to be very useful going forward, because they give us a direction, but when we do calculations for the magnitude, they disappear, and this is the sense in which they disappear. The magnitude is 1, and so it goes away.
Wouldn't C have an arrowhead on top of it then?
It's very useful to realize what we can do with vectors and what we can do with numbers and what we can do with numbers interacting with vectors. So for example, in the calculation of a unit vector, we're taking a vector, multiplying it by a number in front, and then that was called scalar multiplication, and then that gives you another vector. And when you calculate magnitude, that takes a vector and turns it into just a number. When you calculate a magnitude, you're finding the magnitude of a vector. So you start with a vector, do your calculation, and you wind up with just a number. Okay. So operations. Is it possible to multiply vectors? And what would that mean?
Yeah.
Multiply
Okay.
AI with J with K.
Okay. Right, exactly. So we have to come up with the definition of what this means. So it's going to be called the dot product. And first we'll look at the formula, and then we'll look at what it means. So here we go. So for some vectors u and v, u dot v equals that. So you multiply the first components together, you multiply the second components together, and then you add them. Okay. Now this is a dot product for two-dimensional vectors. How does it work for three-dimensional vectors? Exact same idea. It's the product of the first components plus the product of the second components plus the product of the third components. Okay. And naturally, you can extend this to any number of dimensions. Okay. Now, here it comes back to, I mentioned before that we could write vectors using column notation. So using column notation for dot products is really nice because this lets you pair up the matching components visually. U1, V1 plus U2, V2 plus U3, V3. Okay. And a super important point, when you take the dot product of two vectors, what's the result? It's not a vector. It's a number. So the dot product between two vectors is a number. Okay. So let's give this a try. So let's take the dot product of these two vectors, 1, 4, 1, and 2, 0, -3. So what do you get?
2 plus 0 minus 12. 2.
Okay. Let's just write it out using definition. 1 times 2 plus 4 times 0 plus 1 times -3.
That's minus 1.
That's 2 plus 0 minus 3, -1.
Yeah.
So please note that the calculation itself is very straightforward.
This represents the.
Okay. So some properties of dot products. So suppose we have a couple of vectors. Let's say A and B are vectors and C is a number. So what's true? So we have these 4 nice properties that look a lot like properties of multiplication. So first of all, A dot A is the same as the magnitude of A squared. So you got to remember that A and B are vectors. What else? A dot B is the same as B dot A. So it's commutative. Very nice. A dot B plus C is the same as A dot B plus A dot C. So in a sense, it's distributive. Okay? And then finally, if C is a constant, C times A dot B is the same as C times A dot B, and it's the same as A dot C times B. So it's not exactly associative because A, B, and C aren't all vectors, they're not all the same thing, but it's got this associative-like property. But once again, you have to keep in mind what you're allowed to take the dot product between. You're allowed to take the dot product between two vectors, and that gives you a real number. So notice that in rule number 4, the result is going to be a real number because you're always taking the dot product between two vectors. Okay. So each of these properties you can prove just by using the definition of dot products. So, for example, number 1. How can we prove number 1? Well, we could think of A as the vector A1, A2, A3. So when you take the dot product, what do you get? A1 times A1 plus A2 times A2 plus A3 times A3. So clearly that's A1 squared plus A2 squared plus A3 squared, and that's just the norm of A squared because there's no square root there. And you could prove the other rules in a similar way just by writing down the components of the vectors. The dot product has this very beautiful property. Remember, the dot product between two vectors is a number. What does that number represent? Well, its interpretation is this. U dot V equals the magnitude of U times the magnitude of V times cosine theta where theta is the angle between the vectors. So there's your interpretation of the dot product.
You get it radians, right?
So for a property this nice, I think it's surprisingly easy to prove. And the way you prove it is a little cleverness. We use from trig/geometry, use the law of cosines. And you use the vectors u and v and u minus v. And so we talked before, so we had uv and u minus v. We introduced that before as part of a parallelogram. So here we don't need the whole parallelogram, we just need the triangle. And then you apply the law of cosines, and you actually do the calculations with some clever arranging of the terms, and you wind up with this statement. And I'll let you go through the calculations and the algebra. Actually, you know what? This is a really fun proof. Let's do it. Okay. So first we start with this statement. So the norm of, or the magnitude of, u minus v squared. So what is that? Well, you could think of it as u minus v. Let's see. So you could think of it as, first you use the law of cosines. So the law of cosines says u minus v is one of the sides on the triangle. So based on law of cosines, that's like c squared equals a squared plus b squared minus blah blah blah. So it's the one side, which is norm of u squared, plus the other side, which is norm of v squared, minus 2 times the one side norm of u times the other side norm of v times cosine theta. And that's just the law of cosines from trig, I guess. Okay. Now the other way to think about this is to remember that we just decided that when you have a vector, so u minus v is a vector, if you take the magnitude and you square it, that's the same as taking its dot product with itself. That's the thing we just learned. So it's just u minus v dot u minus v. Now we also just learned how to do the dot product like this because everything distributes. That's something else we just learned. So you wind up with u dot u minus u dot v minus v dot u, and then minus minus, so plus v dot v. So you calculate that out, and what do you get? You get u dot u, we now know is the magnitude of u squared. V dot v is the magnitude of v squared. And then we know u dot v and v dot u are the same thing because it's commutative. So we have that it's minus 2 times u dot v. So now you just set the first equation from the law of cosines equal to what we just discovered, because those are both the magnitude of u minus v squared. Set them equal to each other. Cancel out the stuff that's on both sides, and you get u dot v equals norm of u times norm of v times cosine theta. So this is the sort of thing that it'd be really, really difficult to sort of discover on your own, but you can walk through the steps and see that it's just a clever use of a couple different rules, but every individual step is not that bad to follow. So calculation, let's find dot product. Let's use the dot product to find the angle between two vectors. Okay. So here we're in 2 dimensions. So we've got the vector 3, 0 and the vector 0, 5. Now let's find the angle between them. So how do we do that? Well, we're going to take the dot product, and we're going to find their norm. We're going to find their magnitudes, and then we can solve for a cos theta. So cos theta equals u dot v divided by norm of u times norm of v. So we solve for cos theta right in the first step, and then we just solved it out. So the dot product, 30.05, you actually wind up with 0. So on the bottom, you can calculate the magnitudes. So you wind up getting the norm of the magnitude of the first vector is 3, magnitude of the second vector is 5. So it's 3 times 5 is 15, but it winds up just being 0 over 15. So cosine of theta is just 0.
Which means that at right angles.
Yeah.
We already knew that because it was 0 and 0.
Why doesn't the UV have arrows on top of it, on top of the numerator? Cosine theta equals UV.
Okay. Right. So since cosine of theta is 0, therefore we know that the angle theta is pi over 2. So it's a right angle. But yeah, we already knew that. Because what were the two vectors? The vectors were 3, 0, which is on the x-axis, and 0, 5, which is on the y-axis. So, great. So does this always work?
Yes.
Well, the answer is yes, because of the rule that we now have. We now know that the dot product. Where is this? So the dot product between two vectors is the magnitude of the first times the magnitude of the second times cosine theta. Well, if two vectors are at a right angle, that's a right angle, so cosine of that will always be 0. So we have our first nice rule about dot products. Two vectors are perpendicular precisely when their dot product is 0.
Question, is it still valid even if the angle is greater than 90 degrees?
So that's a nice question. So the angle could be, so what does it mean to be perpendicular? So it can be perpendicular like having an angle of positive pi over 2, or perpendicular having an angle of negative pi over 2, or something else. Well, cosine of that angle is still 0. Cosine of positive pi over 2 and cosine of negative pi over 2, that's still 0. So if you like any kind of perpendicular, the cosine of that will be 0 and the dot product will be 0.
No, but what if the angle in general is...
So now we've got a nice fact about vectors, dot product, and perpendicular. So the natural next question is, what about parallel? So what does it mean for two vectors to be parallel? What it means is that they're headed in the same direction. Okay. So remember that same direction, when we think of vectors, we sort of say we can move them anywhere in the plane or in space, and it's still like the same vector. We typically we can always think of vectors as rooted at the origin. So in the same direction, in that case, means that one vector must be a multiple by a number of the other vector. Same direction, but could be a different magnitude. So we get this. U and V are parallel precisely when U is some multiple of V. Okay. So also note that if two vectors are in the same direction, that means the angle between them is 0. So U and V are parallel precisely when the dot product is the product of the norms. Okay. Now to be precise, the angle between them, as we said, it could be like forwards or backwards. So the angle could be 0. The angle could also be pi. So in the case that it's pi, you'd actually have a negative sign in front. Okay. So now let's apply this. Let's answer these questions. So 2 dimensions. The vectors 3, 1 and -6, -2. Are those vectors parallel, perpendicular, or neither? They're parallel, and why is that?
Because the second one is a multiple of the first. -2.
There you go. So noticing that one vector is a multiple of another, it's very easy to spot. Okay. So that's true in this case, so they're parallel. And it winds up looking something like 3, 1, and then -6, -2. So they're on the same line. Okay. Next one. Are these two vectors parallel, perpendicular, or neither? Now we're in 3 dimensions.
They're not parallel.
Okay. They're clearly not parallel. There's no number you can multiply to get one vector to be the other. Okay.
They're not perpendicular.
Okay. So how can we check if they're perpendicular?
We take a U.
So how can we check if they're perpendicular?
We take UV.
You take the dot products. And again, just for organizational reasons, I like using column vectors, especially with the dot products. Okay, so let's take a look. What do we get? 3 times 0 gives 0. 5 times -1 is -5. 1 times 5 is +5. And you get 0. So what's the conclusion? They are perpendicular.
You want to know the arc cosine of 0? No. Wait, hold on. Yeah, right? Arc cosine of 0 gives you 90 degrees, which proves that it's perpendicular. That's correct?
Exactly. Okay. So to calculate that the dot is 0 and therefore they're perpendicular is relatively straightforward. It requires a little bit of mental stretching to think about what this might mean because we're in 3 dimensions. And we're going to come back to the idea of parallel or perpendicular in 3 dimensions, and we're going to come back to that idea. So now we're going to talk about two applications of the dot product. So the first one is a math application. So splitting vectors into components or projections. All right. So, okay. So components. So when we write down vectors in the usual way, we're doing it so that we're writing down the x, y, and in 3 dimensions the z components. So I could ask you a very simple question. Find the x component of the vector 4, 3.
4.
Right. So by inspection, you can just see that it's 4. I want to point out a way that you could do this using dot products. So which vector represents the x direction? No, which vector? Not which component, which vector.
0.
The vector that represents the x direction is the vector 1, 0. So if you recall, 1, 0 actually gets its own notation because it's so important. It's the I vector. Okay. So the 1, 0 vector is the unit vector in the x direction. So what happens when we take the dot product between our starting vector and the vector 1, 0? What do you get?
4i.
You get 4 plus 0. You just get 4. And so that's actually the thing that we want. So taking the dot product with the I vector, which is the unit vector in the x direction, gives us the component that we want. And we're going to use that idea because what if we want the component of our original vector but in a different direction? What if we don't just want the component, what if we don't just want the x component or the y component or the z component? What if we want the component in a different direction?
When you mean by component, you mean the magnitude in this, what do you mean by component? The magnitude, like, what does 4 represent here?
So here's the picture. So in this picture, our original vector is v, or think of v as the original vector, and then think of u as the direction that we're interested in. So before, u was just the x direction or the x-axis or whatever. That's no longer the case. U can be any direction. So we can split v into components. So previously, we split it into components x-axis and y-axis. They're perpendicular. Okay, great. But now we're doing it differently. We're saying, what about the u direction? So we've got a u direction. What we've also got is a perpendicular direction. So there's a nice little notation for that. I'm just going to call that u perpendicular with that little cross there. Okay. So notice that we can say that v, so we can draw a vector in the u direction and then a vector in the perpendicular direction. And then we can say that, so those are components of the, we think of them as components of the original vector. And notice that the first one, the first component, vu, plus the second component, vu perp, if you add them together, you get your original vector v by just the diagram of vector addition, by first going this amount and then going that amount. So that's the sense in which we're breaking down v into components. These two components, such that adding them together gives you your original vector. Now the question is, how do we do that?
How do we do what?
How do we figure out what those two components are?
Oh.
How do we figure out what those two vectors are?
Okay,
So in order to do that,
we know that the angle would be 90 between
So we've got to build them out of the original vector. So first of all, so we've got to find the component or the projection of v in the u direction. So in order to describe any vector, we need to find its magnitude and its direction. Well, we already know direction. So we're going to talk about magnitude direction. Okay. So what's the magnitude? Well, to find the magnitude, look at the picture and think of the triangle.
Okay.
So there is an angle between v and u. So the part of v that's in the direction of u, just think of the triangle. It's the magnitude of v, but times cosine theta. And that'll be like the length of that leg of the triangle. So we know its magnitude is magnitude v times cosine theta.
So we'll do like v
So-
multiplied by cosine of the theta.
Yes. So that gives us the magnitude. Now we just need the direction. But we already know the direction. The direction is the u direction. But remember, we want to have the direction, but we don't want the magnitude from that. We just want the direction. So how do we get quote unquote pure direction? We want the unit vector. So the unit vector is just the direction of u is just the vector u divided by its magnitude. So the unit vector was the thing that we made before. Okay. So, So what we wind up with is the unit vector, which gives us the proper direction, which is the vector u divided by its magnitude. And then we give it the magnitude that we want, which was magnitude of v times cosine theta. So there's the vector we want with the magnitude that we want as a number in front. Now we have to use a little bit of cleverness to work. So you can either leave it like that, the magnitude and the unit vector, or we can rewrite this to get this clever formula.
What happened to cosine?
So where does this clever formula come from? So let's look at the final result. U dot v. What is u dot v? U dot v we know is the same as the magnitude of u times the magnitude of v times cosine theta. So, but the only thing we want is the magnitude of v. So we've got an extra magnitude of u, so divide by the magnitude of u. And when you divide by the magnitude of u, that gives you, we already had one magnitude of u in the denominator, so now we've got magnitude of u times the magnitude of u, which is the magnitude of u squared.
I know this gives you that. I know that much, right? But this part.
Yeah. Okay. Let me also quickly fill in this last detail, because we know that what do we know that so we also know the magnitude of u squared is equal to something. We know that that's u dot u.
Which we can cancel out.
So you actually wind up with this formula, so you can write it just in terms of dot products. Okay. So
Can we cancel out
this
dot
version of the formula is sort of more intuitive, because this part is the magnitude and this part is the direction. But what you see is that when you work it all out, you can actually rewrite it all in terms of dot products. So I just want to confirm that this is actually correct by working backwards. So what is u dot v? U dot v is the magnitude of u times the magnitude of v times cos theta divided by, so u dot u is the magnitude of u times the magnitude of u. And then all this is times the vector u. So what happens? Magnitude of u's cancel. There's your magnitude of v cos theta. And there is your vector u divided by the norm of itself.
Wait, I have a question. We can cancel out the magnitude, but we can't cancel out that one.
So now that we know all that, let's just do a problem. So we've got an original vector. Find the component of -1, 4 in the 2, 3 direction. So the easiest way to do this is by the final formula, which is the dot product formula. That's the easiest way. So let's do it. So first of all, let's keep in mind which is u and which is v. So the first one is v, and the second one is u, because the second vector is the one that's giving us the direction, and the first one is our original vector. So this is, and remember the notation for this is the part of v that's, or the component of v that's in the u direction. So the notation for that is like this. All right. So how do we do this? Well, again, the easy way to do this is using the dot product formula. So it's u dot v over u dot u times the u vector. Okay? So what is, it's kind of in the way right now. Okay. So what is u dot v?
That's -2 plus 12, 10.
So I'm going to be very slow about it. I'm just going to actually write it out. And then all of that times the vector u, which is 2, 3. Okay. So what does this equal? So the dot product on top, -2 plus 12, so it's 10. And on the bottom, 4 plus 9, so it's 13, times the u vector, which is 2, 3. So we've got a number times a vector. Now you can leave it like this, or you can combine it all together, so it looks really just like a vector. So that's going to be 20 over 13, comma, 30 over 13. And maybe that's nicer because it reminds you that it's really just a vector with components. So there you go. So there's the component of your original vector in the 2, 3 direction. So what is this? What does the picture of this look like? Well, it's pretty similar to the picture we drew before. So we've got -1, 4. So that's v in the 2, 3 direction. So 2, 3. So the part of it that's in this direction. So notice that what we're going to get is by drawing the right triangle, what we want is that piece right there. So visually, that's the picture for it, and there's the computation. There's the vector for it, about 1.5, 2.5.
This is gonna sound like a stupid question, but what happens if you were to cancel this out here?
Now, a practical application of the dot product from physics. Force and work. So force and work. So force times distance equals work as long as these things are constant. But now we get into this new idea of where we're applying a force in space. So for example, if you're pulling something along the ground, you're typically not actually getting down on your hands and knees and pulling along the ground, right? Like when you drag a bag of laundry, you're pulling up towards your shoulder, but the bag is dragging along the ground. The only part of your pulling that's actually doing work is the part of the pulling that's going in the direction of the movement, right? So the bag is traveling a distance, but it's traveling a distance along the ground. So only part of the force that's doing work is the part that's in the along the ground direction. So, for example, okay. So what we need, so force is actually has a magnitude and a direction. But now we need to find the part of that that is along the ground. Now we know how to do that. Okay. So a quick update on the notation for force, distance, and work. We usually say work W equals force F times distance D. Only now we have to think of these things. Force now has a direction, and D is now displacement. It has a direction. Okay. So the units for these things are W is work measured in joules. F, now it's a vector. It's measured in a unit that we call newtons, after Isaac Newton. And D is displacement. So its magnitude is in meters, and its direction is just its direction. Okay. So now we have this. So we take the component of the force in the direction that we want is just the magnitude of the force times cosine theta. And that's just from geometry and trigonometry. Times the distance that it goes, which is the magnitude of D. But we now know that magnitude of F times magnitude of D times cos theta is simply F dot D. So using vectors and dot products is a very easy way to write this down. So now let's show how this works in doing a calculation in a problem. Okay. So suppose you're pulling a bag of laundry along with a force of 15 newtons. So your arm makes a 40-degree angle with the ground. So first of all, let's find the magnitude of the force, of your pulling force, which is doing work. And then let's find the actual work done to move the bag 20 meters. Okay. So what's the magnitude of the force that's doing work? So the magnitude of the force that's doing work is not the full F. It's the component of F that's going along the ground, which is F times cos theta. Excuse me. So it's magnitude of F times cosine theta. So we know magnitude of F is 15, but there's a 40-degree angle operating there. So it's 15 times cosine of 40 degrees. And that works out to 11.49. Okay, great. So now we want to find
1.49 newtons.
so we want to find the work done to move the bag 20 meters. So now that we've already found the magnitude, there's another way to find this. The other way to find this, we can simply use force times distance. So the force is 11.49, or the part of the force doing the work is 11.49, and that's newtons. So times the distance, which is 20 meters. So that gives 229.8, and this is work, so that's J for joules. So that's if you first calculate the magnitude. What if you do this problem from scratch? If you do part B from scratch, you can simply say it's F dot D. So what is the force? Ooh. Okay. So notice that in this case, you're told the force at an angle. So this would be a little bit easier if the force was given to you as a vector. So if the force was given to you as a vector and the distance was given to you as a vector, you could then just take the dot product of those two things. Okay. In this case, it's actually given to you as a magnitude and an angle, so it's easier to use the magnitude angle version of the formula. But if the force was given to you as a vector, it's easier to use the vector dot product version of the formula. Does that make sense?